Hello, I'm going to go through the question 1 from the 2015 exam paper. I'm only going to go through the numerical parts. The descriptive parts are on the Word document that's on the Blackboard site as well. Now, first thing to note is have a go at the example first if you can before just jumping straight to the answers. The other thing that is that this question was quite tricky in terms of the amount that was in there, so I did mark it accordingly. So when we're going through this, bear in mind that this is a little bit on the long side for a question. So the first part is about entropy and rubber elasticity. As I say, that's on the Word document answers. The second part then is related to a rubber bridge bearing. Now in this case it gives you the size of the block, 0.8 by 0.8 by 0.5, and it says that the top surface needs to be able to move sideways to accommodate whatever the bridge bearing needs to do. Might be thermal expansion, might be something else. So the block is 0.8 times 0.8 times 0.5, and it needs to move here by 10 centimeters with a force no more than 120 kilonewtons. And the question is then asking what is the maximum chain segment density that it should have. Now what we need to do in this case is work out the stiffness, the shear stiffness of the material that's needed. To do that we need to work out the shear stress and the shear strain, and we have all the numbers that we need for that. So the first part is the shear stress. We know that, as with all stresses, that's going to be the force divided by the area. We know that the force applied is 120 kilonewtons, and we know that the area is 0.8 meters times 0.8 meters, and that comes to equal 1.875 times 10 to the 5 pascals, or 0.1875 megapascals. We also have details for the shear strain. So the shear strain for shear is, if we have a block that's shearing like that, the strain is given by that distance there, which is x, divided by that distance there, y. So x over y, in this case that's 10 centimeters, which is what's allowed as the, or what's required as the sideways movement. The height is 50 centimeters, the height of the block, so that just comes to 0.2. What we then have from those two, we can work out the shear modulus. So the shear modulus, or stiffness, normally called G, is the stress divided by the strain, and so that's equal to 1.875 times 10 to the 5 divided by 0.2, which comes out to be 9.375 times 10 to the 5, or 0.9375 megapascals. So that's our shear modulus that's needed. The question is asking though for the chain segment density. So what we need to do here is go back to our formula sheet, and in the formula sheet there's the in the exam paper, at the end of the exam paper there's a formula sheet, and within that then there's a bit on rubber elasticity, and the thing that's important here is this bit here. So n times k times t is the shear modulus. So we can use that to find the value of n, which is the chain segment density. So what we know is that n times k times t is the shear modulus, so therefore n, which is what we want to find, is g divided by k times t. So in this particular case g is 9.375 times 10 to the 5, keep everything in basic SI units here. K, the Boltzmann's constant, is 1.38 times 10 to the minus 23, it's given in the formula sheet if you can't remember it, and T, the temperature, is 23 degrees, so that's 296 Kelvin. And if we work those out, that comes to equal 2.30 times 10 to the 26. Now it's a very big number, but we would expect a big number because this is the number of chain segments, so the number of chain bits within a cubic meter. So the units for that are per cubic meter. So that would be the answer for that second part. The third part then, we're now looking at the vertical compression. It says second block, same size but different shear modulus. Just in case you hadn't calculated a shear modulus in the first part, it gives you a different one here, so you're not relying on a value from the first part. In this case it's supporting a vertical compression load of 160 kilonewtons, and the limit on the compressive displacement is is 2 millimeters. So in this case what we're doing is we've got the compressive load of 160 kilonewtons and we need it to compress by no more than 2 millimeters. Again, it's a case of working out the stiffness that's needed. In this case though, what we need to do is then work out how we get that stiffness with the shape factor. So go through it a bit at a time. The compressive stress that we have is the force divided by the area, which is 160 kilonewtons. Oops, I've got an extra naught in there. Get rid of that. 160 kilonewtons divided by the area, which is 0.8 meters times 0.8 meters. And that equals 2.50 times 10 to the 5 pascals. What we also then have is the compressive strain, which is the, if you like, the displacement divided by the original length. So in this case it's 2 millimeters, which is what we're allowed, divided by the height of the block, which is 500 millimeters, 50 centimeters or half a meter, and that comes to be equal to 0.004. So then what we have is the compressive stiffness that's needed. Let's call it EC, is the stress divided by the strain, which is 2.50 10 to the 5 divided by 0.004, which comes to equal 6.25 times 10 to the 7, or 62.5 megapascals. Now we've got a shear modulus of 1.5 megapascals, so we've got to try in some way of get to a compressive stiffness of 62.5 megapascals, much bigger. And the way that we'll do that is to use the fact that we can use laminations. Now this question also asks for a descriptive part as to how laminating the rubber can help to achieve a high stiffness. I'm not going to cover that in this video example because it's covered in the Word document. So again, have a look at that as well. But the principle behind it is that if we can make lots of thin layers, each of those thin layers is constrained from shearing sideways, so it actually has a higher compressive stiffness within the layers because the shape is constrained. The fact basically that if you have a rubber block that's bonded at both sides, if it's wide and thin, then it has a much higher effective compressive modulus than if it's tall and narrow. There is a formula for the shape factor effect on the modulus here, which is this one. So the compressive modulus is G times 3 plus 5s squared. So I'll just copy that across so that we've got it here. Just move it so that it's visible. So what we have here is that we know that the compressive modulus is G times 3 plus 5s squared. So that will mean that compressive modulus divided by G, which we know is 62.5 megapascals divided by 1.5 megapascals, which is equal to 41.67, is equal to 3 plus 5s squared. From that then we can work out what S must be, and if we rearrange that a little bit and work out S, comes to 2.78. Now S is the shape factor, so that's defined as the loaded area divided by the free area, so the load free area. Now in the case of our block, what we've got is we've got each layer has a size of 0.8 times 0.8, and the thickness is T, because that's what we need to try and work out. So the loaded area will be equal to 0.8 times 0.8. The load free area, there's 4 sides, so there's 4 there. Each of them is 0.8 meters long, and each of them is T high. And rearranging that, then that must equal to, so that must equal to 2.78. Rearranging that gives us the fact that T must be equal to 71.94 millimeters. And And what we have with the block is we have our block, which is it's not asking, the question isn't asking for the number of the thickness of the layers, it's asking for the number of layers. So the number of the layers is the height of the block, which is 0.5 meters, divided by t, so that's 500 millimeters divided by 71.94 millimeters, and that comes out to equal 6.9. Now we obviously can't have a non-integral number of layers, we have to have a whole number of layers. So the question is, do we need 6 or 7? Well, the thing to think about in the question is that the question has to have no more than 2 millimeters compression with 160 kilonewtons. So we need a compressive stiffness of at least this value here, 62.5. Therefore, if we have more layers, we'll have a bigger shape factor with thinner layers, and that'll give us a higher compressive stiffness. So we need to err on the side of caution, so we need 7 layers. And each layer would be 71.43 millimeters thick. So that's the answer that we need to get to.